Welcome. We are studying potentiometers, AC potentiometers particularly, and the important issue about AC potentiometer is that the phase angle of the unknown source matters. Okay. So, we have seen how to take care of this phase angle using a polar potentiometer, and we are going to see another type of potentiometer, which is coordinate potentiometer, with which we can again measure unknown AC voltages with arbitrary phase angle. Before we come to this, let me motivate you by saying that an AC voltage can be represented as a complex phasor that you know, a complex number. Okay. Now, a complex number can be represented in two forms. One is A plus IB, another is R angle theta, or this is magnitude and the angle. Okay. So, we can represent a complex number in two forms. The polar potentiometer measures the unknown voltage in this form, magnitude and phase angle. The phase angle is read from the dial of the phase shifter and the magnitude from the length at which the null point is obtained. So, this is the motivation, or this representation is the motivation behind polar potentiometer, because this is also called polar form of polar representation of a complex number. And this is the motivation of today's topic, coordinate potentiometer. So, today the potentiometer that we will see will measure the unknown voltage in this form, A plus IP. Okay. So, basically we need two potentiometers, one to measure the real part of a complex voltage, another to measure the imaginary part, so to say. So, we need two potentiometers. So, let me draw them like this. This is one potentiometer wire and this is another potentiometer wire. Now, the way we will do it is this. So, we will supply we will apply two voltages, of course, two AC voltages, in a one here, another here, in a way so that this two currents, okay, say this current and this current, call it I1 and I2, they are at 90 degrees phase angle. Okay. So, this is not what I am drawing now, is not the complete picture, but just to motivate you for now. Let me have just two voltage sources, such that the two currents are 90 degree out of phase. Okay, so we have to somehow we have to ensure I1 and I2 are 90 degree out of phase and of equal magnitude. Okay, so then it will actually mean that, okay, so these two are identical potentiometer wires. So the length of this and the length of this maybe are same. Their resistance per unit length may be same. So if we can adjust I1 and I2 to have 90 degree phase angle, then we can ensure that the voltage drop in this wire and this wire, they are also 90 degree out of phase, and the voltage drop per unit length will also be same. Okay, so this will actually ensure, okay, let me write it directly. So we have to ensure that voltage, call this voltage V1, and this V2, lengths are same. The potentiometers have same length. So let's ensure that V1 and V2 are 90 degree out of phase and with equal magnitude. For that, basically you have to adjust this I1 and I2 somehow. You have to adjust this here and here to make I1 and I2 such that V1 and V2 90 degree out of phase and of equal magnitude. Okay. Now let me have the unknown source. So the unknown source is here, Vx, x means unknown, and what we will do is we will connect two jockeys like this, one through a galvanometer, one here, another here. Okay, and let me sort these two terminals. Okay, so these two terminals are sorted. You can take this point as the reference for calculation. This is the reference point. Okay, so now we have to adjust this and this during the measurement to get a null in this galvanometer. So during measurement we have to adjust both, call this J1, jockey 1 and J2. We have to adjust J1 and J2 together to get null here in this galvanometer. So that means no current should flow through this. When is that possible? That is possible only if this, in this circuit, the voltage, total voltage is 0. Okay. Now if this, let me call this voltage from here to here, from this reference point up to this side, call this V L and call this voltage as VR. Then what can we say? Okay, and the reference direction, so this is 0 side, so VR is measured like this, VL is measured like this, VL is measured with respect to this point, VR is also measured with respect to this point. So then we can say, and Vx, let me take the reference of Vx like this, for example. Okay, so then we can write applying KVL starting from here. So we have VR. Okay, so this is KVL. VR, then minus Vx, and then minus VL. This is equal to 0. Right? VR rise, Vx drop, VL drop. So VR minus Vx minus VL equal to 0. So then this implies Vx is equal to VR minus VL. Okay, VR minus VL. Now, what is VL? VL will be, so if this length is capital L, here also it is capital L, and this length from here to here, this length, call it L for left, and here length right, left and right potentiometer. Okay, so then we can write this as, so VR will be equal to V2 divided by L multiplied by LR minus VL is V1 divided by L multiplied by L left. So this is the unknown voltage. And now we have made sure that V1 is out of phase with V2 by an angle 90 degree. So we may write that, say, V2 is equal to I V1 plus or minus. Okay, so there will be a plus or minus. So plus minus sign we have to somehow decide. So let me just put this note, we'll think about it later. Okay, so if we know this value, if it is plus or minus, then this I is root over minus 1, complex I. Then we can write this as here V1 by L, this is V1, V1 by L, LR multiplied by I minus V1 by L, L. So this is Vx. Okay, so you see we are getting the unknown voltage Vx in this form, A plus IB, where this is A, okay, V1, this is A, this is B. So this is the principle of this coordinate potentiometer. This is the basic principle. Okay, so you must understand this much before we proceed further and talk about more details like how to get these two currents, these two voltages 90 degree out of phase, how to ensure that yes, they are exactly 90 degree out of phase, their magnitudes are same. So we will talk about this, but before that you may take a pause and make sure that you have understood up to this. If you have understood, then let us proceed and ask how to ensure or how to obtain or ensure that magnitude of V1 is same as the magnitude of V2 and the angle between V1 and V2 is 90 degree. So, this is the question. Okay. So, what we will do is this. Just like we did it for the polar potentiometer, we will take a source and supply this side and this side with one side through a capacitor, resistor, something to change the phase angle of the respective current between the respective currents. So, what we will do is this. Let me first put say a transformer here. So, this is a transformer and let me supply this transformer like this. If you want to control the current or the voltage of this, okay, and finally we have to control this voltage, the magnitude of this voltage. So, we may need to put some resistance. You can put it here, you can also put it in the secondary side. Okay. So, by controlling this resistance also you can control this current and thereby this voltage. You can have a resistance here as well. So, in principle both are okay. And here this side we will again, let me take a transformer, but let me feed this through a variable capacitor, resistor or some sort of impedance with which you can control the phase angle of this current and thereby the phase angle of the secondary voltage, thereby this current and so this voltage. Okay. Okay. Now, so this can control the magnitude and phase angle between the V1 and V2, can control the angle between V1 and V2. Okay. So, you have to adjust this until and unless you get these two voltages V1 and V2 at 90 degree out of phase and same magnitude. So, this is the control, how you can control, how you can change the angle. But the next question is more important question, how do we know that we are at the desired condition, that we have obtained correct phase angle and correct magnitude? How do we test that? So, for that So the way we will do it like this. So let me tell you the entire procedure, how to use it, starting from the calibration. Okay. So let me tell you the entire procedure in detail. So first step is to calibrate steps. So step 1, calibrate this potentiometer. Okay, call this PL, pot L, left potentiometer. Calibrate pot L. How? So for that we need a standard cell, DC standard cell. Okay, so what we will do, okay, so let me make several copies of this. Okay, so step 1 is calibration of potentiometer 1. For that, let me, so we do not need this unknown source right now. So let me erase this unknown source. So what we have to do, we have to connect the standard cell so if we are taking this as the reference point, so let's connect the standard cell like this. Through a galvanometer. Okay, and so first decide the suitable length where you want to get the null. So that is decided by the choice of voltage per unit length that you that in turn depends on the magnitude of the unknown voltage. You should have an idea of the magnitude of the unknown voltage. So you decide. So decide the voltage per unit length accordingly. Put the jockey, call this J1, then put jockey J1 at a length. So from left, this is now from the right side. Okay, so put jockey at a length, call it L, such that, okay, so decide the volt, if this is V volt per centimeter say, then put the jockey at a length L centimeter such that V volt per centimeter multiplied by L centimeter is equal to the standard cell voltage VSTD. Okay, put it there. and then adjust say this resistance or this resistance, call this one R1, R2, adjust R1 or R2 or both to get null. Okay, that means the potentiometer 1 or potentiometer L is calibrated, calibration is over. But of course, we need to record the value of this ammeter here. Okay, so record the value of ammeter A1. Say this is equal to I1. Okay, so note this value, and then the calibration of potentiometer 1 is done. Now next step is calibration of potentiometer 2. Okay, call it pot R. So this is pot R, right pot L, pot R. Okay, now for that what we will do, and then we have this ammeter A1, of course, and here we will put a new equipment. What is that? That is going to be a air core transformer. Important that this should be air core. Okay, so I am not drawing any core. So this is an air core transformer. Okay, and so if any current is flowing here, then we will have some voltage induced in the secondary. This voltage we will bring and connect one side here, another side through the galvanometer we will connect it here. This is movable. Okay, now we need to know the mutual inductance of this this transformer, or that means between these coupled coils. Okay, and now observe that this voltage in the secondary, call this Vm. This voltage in the secondary is at 90 degree with the current which is flowing here or here, I2. Okay, Vm must be 90 degree out of phase with I2. Why? Because what is Vm? Vm is nothing but dd, so it is it is proportional to m multiplied by d dt of I2. Okay, or for AC we can write this as j omega m I2 I2t, and this is the RMS value. Okay, so Vm is 90 degree out of phase from this current. Okay, now this voltage V2 is in phase with I2. V2 and I2 are in same phase. Why? Because this wire is resistive. Okay, since this circuit is resistive, so V2 is nothing but I2 multiplied by some resistance. So V2 and I2 are in same phase, and Vm and I2 are 90 degree out of phase. Now these two facts together, what does it imply? Vm and V2, they will be 90 degree out of phase. Okay, so this fact that Vm is 90 degree out of phase from I2, but I2 is in same phase with V2, this implies that Vm is 90 degree out of phase with V2. Okay, now if we can make V2 90 degree out of phase from V1, if we can make V2 90 degree out of phase from V1, then Vm and V1 will be in same phase, same or 180 degree out of phase. So will be in phase. Okay, because if we can make V2 90 degree from V1, V2 is 90 degree from V1, and Vm is 90 degree from V2, that means V1 and Vm will be either in 0 degree or 180 degree. And then only we can get a balance here by moving this jockey. So here actually we are bringing this Vm to potentiometer 1 and measuring this Vm using potentiometer 1 or potentiometer L. Okay, and we can get a balance or null only if we can make V2 90 degree out of phase of V1. Okay. And then only we can get a balance of Vm with potentiometer L. Okay. So if we do not get any balance, if we fail to get any balance for any position of this jockey, that means Vm is not in phase with V1, which in turn will mean V2 is not at 90 degree with V1, and then we have to adjust this things, this capacitance, this resistance, okay, so that V2 is 90 degree out of phase from V1. So let me write. So if we fail to get balance, then we have to adjust this capacitor, call that C3R3, C3 and R3, and once we adjust it so that we get a balance, that ensures V2 and V1 are 90 degree out of phase. Once we get balance above, in the above procedure, then V1 and V2 are 90 degree out of phase as desired. Okay. And also if we know the value of M, if we know the if we know the value of M, then from Vm we can estimate this current I2. If we know the value of Vm, then we can estimate the value of this current I2 from Vm, and then from that we can estimate the value of V2 if we know the resistance of this wire. Okay. So, now say if this is M, then from the value of Vm, how can we get the value of I2? I2 is, so let's write I2 is same as Vm, or let's write it this way. Vm is equal to j omega m. Omega is known. If m is also known, we can write this j omega m multiplied by I2. Okay. And say we want this total voltage V2 to be equal to V1. So we want V2 equals V1 magnitude. Okay. So, and from here we can write that the magnitude of Vm is same as m omega magnitude of I2, and we can also write V2 is equal to R times I2, where R is the resistance of this potentiometer wire. Okay, so we can write V2 is this. Okay, all these are magnitudes. So then we can write, so this is what we want, V2 is equal to V1. So in place of V2, we write Ri2 from here. This is equal to V1, and in place of I2, let us write Vm by m omega. So V1 will be Vm multiplied by R times m omega. Okay. So if we know this factor, so we need to know this factor. We need to know this factor, or maybe the potentiometer manufacturer or the seller will give us this factor, okay, for a particular value of omega. Then we know that for which length here, so for what value of this length called this L, what call this x. I might have used L many a times. Call this x, this length. Okay. So what will be the value of this x? Okay. So we can write that so we are getting Vm here, and we want to get a balance. Okay, so we want to get a balance, and to get the balance at length x, we need to satisfy V1 by the total length L, this total length L multiplied by x is equal to Vm. Okay. So now from this equation we can write that, so these two equations will imply that V1, this V1 is equal to Vm. Now Vm is same as this. Okay, multiplied by R by m omega. This is known. Now this 2 cancels, so x will be L multiplied by m omega by R. Okay, so what we have to do is we have to put the jockey at this particular length x and adjust these values, these two values, or you can also adjust this resistance to control the total current. Okay, call this R1, R2. Okay, so x is obtained like this. Now so what we have to do is set the jockey at x equal to L m omega by R. Okay, this factor m omega by R should be known. So set the jockey there and adjust. What we can adjust? We can adjust C3, R3, R2. Adjust C3, R3, R2 to get balance. Do not move the jockey at this point. Do not change anything in the fast potentiometer. Okay, do not change R1 or this resistance. Don't change anything, or in one words, do not change this current I1, which is fixed in the first step. Do not change I1. This is most important. Once we get the balance, the calibration of the second potentiometer is over. That means we have made sure the voltage V2 is in same phase with, out of phase from V1 and same magnitude like V1. So, this is step 2 over. Now, final step, step 3. This is the measurement of unknown voltage. Okay. So, in this phase, we will still have this, of course, this is always there. Here also we will have this, although we are not using it. So, you can keep it open. Here also you are not going to, in this measurement phase we are not going to use it, you can keep it open, but okay. And now we will connect the Vx, okay, and we will have two jockeys. Okay. So, do not change I1 and I2. That means do not change anything. So, this is R1, this is R2, C3, R3. Okay. So, do not change any of this R1, R2, R3 or C3. Do not change any of this. Move the position of J1 and J2 to find null, and once we have the null, then we can write that. So, at null we can write that Vx is equal to Vx is how much? This is, so we can write once again the KVL so Vx plus Vr minus Vl is 0, Vx plus Vr, Vx, Vr, minus Vl is 0, implying Vx is equal to Vl minus Vr, and now Vl and Vr can be found from these two lengths. Okay. So, that is the process, that is the total entire process. Okay. So, maybe I recap a bit. V1 from here, okay, sorry, Vx from here is this. Okay, so let me write J to be consistent. J means root over minus 1. Okay, so now you can put this value here for VL and VR, so you will get Vx, and we are done. Okay. So, let me just conclude this video by summarizing it in brief. So, what we have to do is first decide the per unit length voltage that we want to have. Then we have to set the standard, connect the standard cell to the potentiometer, keeping in mind the chosen value of voltage per unit length. Find the null, that is calibration of potentiometer 1. Then using the air core transformer, we have to calibrate the second potentiometer. Once again, we have to first decide at which point the null should be obtained, put the jockey at that position, adjust the capacitance and resistance to change the phase angle and magnitude of the second potentiometer. Once we get the null, we are done. Phase 3, last phase, connect the unknown voltage across the two potentiometers together. Adjust the two jockeys, do not change anything that can change the current in either potentiometer 1 or potentiometer 2. Change only the two jockeys, find the null, and from the lengths get the voltage. So, one small but important thing which I forgot to mention before is why we use air core transformer here. Why not iron core transformer? Okay. This is because in case of iron core transformer, the flux is not exactly in the same phase with the primary current. There is a small delay which we call the hysteresis lag, due to which the flux generated by this primary coil, which is this I2, and so I2 and flux, they will have a small lag between them. Therefore, this secondary voltage Vm will also not be exactly at 90 degree from the current I2. Okay. But in case of air core, there is no hysteresis lag, and that is why this transformer must be air core. That is important. Okay. Another small thing, you observe that the voltage induced in the secondary is, the voltage here is Vm, and at the null condition, when there is no current in the secondary circuit, then there is no voltage drop also in the secondary. So, therefore, the voltage that we are getting here is strictly Vm. There is no voltage drop at all in the secondary. This is also a nice thing, nice and obvious thing. So, the voltage that we are measuring, that is coming here, is exactly 90 degree out of phase from this current I2. Okay. So, this is also important. So, since we are dealing with the subject of measurement where accuracy is very crucial, important, these minute things must be remembered, that we should not use a iron core transformer here. Okay. Thank you.